Yeah. So this is what we have seen yesterday, method of successive approximations, wherein we approximately take something called zeroth approximation y0 of x. In this case, we have taken that zeroth approximation to be your function fx. Then your first approximation was depending on your zeroth approximation. Then your second approximation was depending on your first approximation, and likewise your mth approximation ym was depending on m minus 1th approximation, right? So let me hide this also, let it be. And then if the limit of this ym converges to some y tilde, then this y tilde will satisfy your given equation 1, and hence that will be the solution of your integral equation. And then we started with equation number 2, that is for y2, and then you substitute for that y1, simplified, and then we got this k1, k2, then for next we got k3, we'll hide this, we got k3, then in general we got ki's, and we have written your ym as ym of x is equals to fx plus summation I from 1 to m lambda raised to I something. Now this is through your observation. We have found your y1, y2, y3, and then we generalize this. Where this ki of x comma t is, we have taken this, and I told you to check whether both are same. That's your job. And this ki of x comma t is called ith iterated kernel. When you take this limit of ym, you will have this infinite series, and this infinite series is called Neumann series. Now the next problem was whether the given series converges or not, or for what lambda, or for what conditions, under what conditions the given series converges. That is what you have to discuss. And yes, anybody got understood the proof already there on your text? Anyone at least tried?
So I didn't find it on Lysenko, yes, sir.
It is there on Kanwal, Ram Kanwal.
Okay.
Anyways, I will do it for you. You just see this. Now you consider this. Let me write this mod of integral a to b km x comma t ft dt the whole square. Now you can use some inequalities which we will study in functional, or you might have already studied in your linear. This entire the whole square is less than or equals to this. You find the name of that inequality. You might have already seen that. Km x comma t the whole square dt, and integral a to b, the second function, mod of ft square dt. Anybody knows what is the name of this inequality?
Sir, squares inequality.
Are you sure?
Sir, yes. Yeah.
What is the name of this inequality? You find it out. Verify. Now what we do is we take, let norm of f the whole square is equals to integral a to b mod of ft the whole square dt. For that you should know what is norm and what is inner product on that space, L2 space. We have stated that this f belongs to L2, even that k belongs to L2. That means those are square integrable function. That means this will be finite. And on that you define norm by norm of f is equals to this bracket integral whole raised to half. So I am taking square on both the sides, then raised to half I am taking this side. So it is norm of f the whole square is equals to this, right? And this is equals to, let us take this to be some d, and d square, d is constant. It's finite because f belongs to L2 class, right? And then this km, so obviously if you want to find some bound for this, it will be based on your m. If I change my m, my upper bound or lower bound will change. It's based on that. Alright? 1 minute.
Yes, sir.
Okay, so if I want to take this bound, it will be based on this m, right? So let us take this cm square. You need not take this m square and a square on both the sides or something like that. But if you take square, this d square, cm square, that will help you in the next calculations. So let us take these squares. So cm square, you take this as upper bound of integral a to b mod of am x comma t the whole square dt. So this we have taken, this is finite, we know, so we have taken this as d square. And for this you check, I told you to check if the kernel belongs to L2 function, L2 class, then what are the conditions. So you take the cm square as the upper bound of this integral. So with this 2, we will get this integral mod of integral a to b km x comma t ft dt the whole square is less than or equals to, we have it cm square d square. Mark this as equation 1. Very simple thing. What we have done is we have taken this mod of ft the whole square, that integral, as a d square because it's finite, and this is bounded, or its upper bound is cm square. So obviously this, both the integrals will be less than or equals to cm square into d square, right? So we get this equation 1. Now also we know that what is km. Km xt is nothing but integral a to b k x comma u k m minus 1 u comma t du. This is your definition, right? So if you take the square of this, therefore if you take mod of km xt the whole square, you will have square of this, right? Mod of this and then square. And again, by using the same inequalities, you will have less than or equals to this one and this one. So let me write this way: integral a to b. You can take this first or this first. We have stated that. This with the same. So this will be equals to, should I change it? Anyways, none, it doesn't matter. So this is mod of km minus 1 x comma u whole square du is 1, and then the second one is integral a to b mod of k u comma t whole square du. Again, the question is, what is the name of this inequality? Alright, now this is less than or equals to, now we have stated that The Cm square is the upper bound of this mod of Km integral, and in this case we have mod of Km minus 1 square integral. So this will be bounded by Cm minus 1 square. This from here we have taken Cm square as the upper bound of this integral with Km m. So if you change this m minus 1, you will have Cm minus 1. Right? So this is Cm minus 1 whole square, and then this integral a to b mod of k u comma t whole square du. And when you take integrals and all, you will have, this implies integral a to b mod of km x comma t the whole square dt. You integrate this with respect to t, this will be less than or equals to obviously this constant Cm minus 1 the whole square. Then we will have double integral a to b mod of k u comma t square, this du, and then dt. And let me write here itself. This will be less than or should I write directly? This is equals to Cm minus 1 the whole square into b square. Now what is this b square? B square is nothing but this integral. Since we said that this k is L2 function, this will be finite, this integral will be finite, and then the value of that integral will be some constant number, and I am taking that constant number to be b square. So let me write here what is that b square, where this b square is equals to integral a to b mod of k u comma t the whole square du dt. Clear? So right, so what we got is, this implies we have Cm minus 1, or we have Cm the whole square is less than or equals to okay, I can put this in another language. If you see this integral is bounded by the Cm minus 1 the whole square into b square, both are constant. So when you take the upper bound of this, again it will be bounded by the same numbers, and we have taken Cm, we have taken Cm square as the upper bound of this. So obviously if you take the upper bound here, that is Cm square will be less than or equals to this quantity. So that is what I am writing now. So Cm square is less than or equals to b square into Cm minus 1 square. Right? Now again you use the same inequality for Cm minus 1, it will be less than or equals to b square is there, and the Cm minus 1 the whole square will be less than or equals to b square into Cm minus 2 whole square. Likewise it will be less than, and finally you will have b square into something, and finally you will have C1 square. Can you tell me what will be this? Cm minus 1, Cm minus 2, Cm minus 3, so up to 1 you will go. So how many b squares will be here? That is the question. How many b squares will be there? Or in simple language, we are not audible.
So m minus 1 b square.
Total b square raised to
Yes, sir.
m minus 1.
That will be m minus 1 b.
Yes, that is b raised to m minus 1 the whole square. Raised to, not into. Right? So altogether I can write this same as b raised to m minus 1 c1 the whole square. You take squares on both the sides, this common, and then you write it with the laws of indices and all. So with this inequalities, your equation 1, using equation 1, we have this integral, we have this integral from equation 1, ab km x comma t ft dt the whole square. This entire thing will be less than or equals to that d square was there, and then your HCM just now we have calculated, it is b raised to m minus 1 into c1 the whole square, right? And then this will imply these quantities are positive. There is to be am x comma t ft dt is less than or equals to d b raised to m minus 1 c1. Right, now when you have this Neumann series, it has this integral and then lambda raised to something. So this implies in Neumann series, you have this Neumann series, you have this summand, the summand in the summation is such that lambda raised to m a to b a m x comma t f dt this is in your summation, and then this was or this is less than or equals to lambda raised to m. So what you are doing, you are multiplying this equation by lambda raised to m, and that will be your summand. So lambda raised to m, I will adjust somehow b raised to m upon b, because already we have b raised to m minus 1. So you multiply by b, then you have c1, and then you have d, right? And this is same as lambda b raised to m c1 d upon b. Now this summation has this summation, so you can use Weierstrass tests, and you can say Weierstrass test for convergence, summation m from 1 to infinity lambda b raised to m c1 d upon b. Now if you see here, the c1 is constant, d is constant, b is constant. Your convergence or divergence will not be depending on this, it will depend on this, because it depends on the power m. Now this series converges if, what is the condition? This is the series. When this series converges, when the series summation of x raised to n converges, when the series of x raised to n converges.
So if x is less than 1 or something. No.
Yes, so yeah, that's correct. Mod of lambda b is less than 1. In this case, your x is nothing but lambda b. So b is less than 1, and we know that b is a positive number. So this implies that is lambda mod of lambda b less than 1, right? So this series converges if mod of lambda b is less than 1, and hence by Weierstrass test we can say, by check the test. I'm not going to discuss all, we don't have that much time. So by Weierstrass test, Neumann series converges if mod of lambda b is less than 1, right? Now if mod of lambda b is less than 1, therefore that series converges. We can write this as y tilde of x to be fx plus whatever we have. That lambda is to something. I will take that lambda, one lambda out, so lambda, then we will take this integral a to b. We can interchange. I have to check now Neumann series. Yeah, here. So if this integral okay, if this series is not convergent, then we cannot interchange this. Or in short, you find out the conditions wherein this infinite series and this integral when you interchange. Now in this case I can write that integral outside and then summation inside. 1 to infinity. 1 lambda I have taken out. So this is lambda raised to I minus 1. I have taken I, so lambda raised to I minus 1. ei x comma t ft dt. And then you just note this. This is same as fx plus lambda integral a to b. You write this as gamma x t lambda, this entire series with these things ft dt. And this gamma x t lambda, this is called right here. This gamma x t lambda is called resolvent kernel. So if you want to find the resolvent kernel, you can go with these iterated kernels, get the summation of this series, and that series is called the resolvent kernel. Now my question is, show that or show the uniqueness of solution. So whatever solution you will get, it's a unique. So your question is, show that this whatever solution you got is unique. So with this we can state a theorem. Whatever you have discussed, for that we can state a theorem. To each L2 kernel, I told you to check what is the meaning of L2 kernel. Kernel is a function of two variables. So to each L2 kernel kxt, there corresponds unique. So this is a question. You have to show that it's a unique resolvent kernel. And if you have unique resolvent kernel, obviously we have a unique solution. Unique resolvent kernel, we have denoted this by gamma x t lambda. Yes, which is an analytic function. What is analytic function? Which is an analytic function of lambda. Now if you see here, gamma xt is lambda is a function of three variables. So this gamma xt lambda is analytic function of lambda. X we don't know. Alright, is an analytic function of lambda. Then there is something called as regular. regular at least inside the circle we have that mod of lambda b less than 1. So mod of lambda is less than 1 by b, and represented by the power series gamma x t lambda is equals to summation I from 1 to infinity lambda raised to I minus 1 ai x comma t. Alright, be careful, we have taken that 1 lambda outside. When you solve the integral, we have taken 1 lambda outside, and then in summation it is lambda raised to I minus 1. So it will be first k1, then lambda k2, lambda square k3, and so on. So be careful there. So gamma xt lambda is summation is nothing but the summation lambda raised to I minus 1 ki x comma t is this. Furthermore, we complete here itself. Furthermore, if fx is also L2 function, then the unique L2 solution of the freedom, let me go on the next page, of the freedom equation 1 valid in the circle is mod of lambda is less than 1 by b. So you are not taking the boundary of that circle. Is given by y of x is equals to fx plus lambda integral a to b gamma x t lambda ft dt. Alright, so this is theorem. There are some points which you have to remember here. Some drawbacks you can see. The first is computation of Neumann series is time consuming. You need lots of time to get these KIs, and then you get the series, then you have to find the consuming, and some cases you can find, but in general cannot be obtained. In general you cannot obtain in terms of some known function. Sometimes you can get the known function, like you will get the series of e raised to x, or you will get the series of sin x. So if you know the standard form of this series, you can directly write what is this called this kernel, but without kernel. But sometimes you will get a series wherein you don't know the standard form of that series. So that is one of the drawback. And secondly, that here only. Secondly, the integral equation 1 will also have.
So your voice screen is stuck, sir. So screen is stuck and your
Yes,
voice
yes,
is
yes.
getting stuck.
So discussing. Yeah. So integral equation 1 my screen is visible, yes. So integral equation 1 will also have solution when this mod of lambda is greater than 1 by b. So these are the 2 points wherein there are some drawbacks you can say for this Neumann series. So first thing, as I said, you may not get the standard function, which is known function. And secondly, what we said is inside the circle you have a unique solution. But again, outside the circle also you may have a solution. So these are some points which I said. First, you may not get the standard function, and secondly, you may also have a solution outside that circle. The theorem stated that inside the circle you have a solution here, but again in outside the circle also you may have a solution, right? Let us take some examples straight away. Solve the integral equation or we can say find the resolvent kernel. We have stated that it's a unique, so I can say find the resolvent kernel, right? And the equation is y of x is equals to fx plus lambda integral from 0 to 1 e raised to x minus t y of t dt. So for this integral equation you have to find the solution, or in other words you have to find the resolvent kernel, right? You can start simultaneously, but let me write this. Here we have k x comma t as e raised to x minus t, and so we know what is k1. Now in this case resolvent kernel means everything is based on your this one, what can I say, ki's. It all depends on your ki's. Lambda, you know, in this case your lambda is already there, right? Am I audible?
Okay, sir.
Okay, so your kxt is nothing but e raised to x minus t, right? So let your k1 x comma t, we have taken that k1 as k, so k1 is same as k xt, and that we have here as e raised to x minus t. Now find what is k2. K2 x comma t was integral, in this case a and b are 0 and 1 respectively, so integral from 0 to 1 we had k x comma u, then k2 depends on k1, so k1 u comma t du. You have the function k, again you have the function k1, so substitute the values accordingly. You will have integral 0 to 1 k of x comma u will be e raised to x minus u, and then k1 is u comma t, so e raised to u minus t du. When you plot these terms together, you will have e raised to x minus t du, and you are integrating with respect to u. You are integrating with respect to u. In the integrand, there is no u, so this will be equals to e raised to x minus t, and when you integrate, you will have 1. So we have this k2 of xt is e raised to x minus t, e raised to x minus t. So based on k2, again we have to find k3. So for k3 of x comma t is equals to integral 0 to 1 k x comma u k2 u comma t du dt is du. This is same as integral 0 to 1 e raised to x minus u. K2 was same, so k e raised to u minus t du. This is same as integral 0 to 1 e raised to x minus t du, and this is same as e raised to x minus t. Now again, if you have noticed, we have k1 is equals to k2 is equals to k3. So in general, we can generalize here. If not, you can find the next terms. In general, our km of x comma t or ki of x comma t will be same as e raised to x minus t. So once we have the generalized kernel km or ki, we can go for the resolvent kernel. The resolvent kernel is given by gamma x t lambda is equals to, we had that summation, say I from 1 to infinity lambda raised to I minus 1 ai x comma t. So this was same as summation I from 1 to infinity lambda raised to I minus 1, and our ki's or km's was e raised to x minus t. This is same as e raised to x minus t. We can take out summation I from 1 to infinity lambda raised to I minus 1. So this is your resolvent kernel, and again you can get the value of this summation. You can write it as e raised to x minus t upon 1 minus lambda, provided there are some conditions on lambda. And once we have this, we can say the solution, and the solution is given by y of x is equals to fx plus lambda integral 0 to 1 gamma xt lambda, that is e raised to x minus t upon 1 minus lambda ft dt. So this is how we got the solution, and we got the resolvent kernel. Next, I will give some examples for you to solve. You try it. Exercise, I should say. Exercise. Find the resolvent kernel can find solution also. Kernel of y of x is equals to 1 plus lambda integral 0 to 1 1 minus 3 xt y of t dt. So try to find the solution. You try to get the resolvent kernel as well. And one more I will give. Find or solve the integral equation y of x is equals to 1 plus lambda integral from 0 to pi sine x plus t y of t dt. So for this you find your resultant kernels and get the solution. Let me give the next. Solve the integral equation y of x is equals to 2x plus lambda integral 0 to 1 x minus t y of t dt by method of successive approximation to the third order. That means you have to find up to y3, third order. And last, solve the integral equation y of x is equals to 1 plus lambda integral 0 to 1 1 minus 3 xt y of t dt by method of successive approximations to the third order. So you try to solve this up to third order. So try to get these solutions. In the next class we will see some other modified methods to get the solution.